Please welcome Dr. Gavin Wood.
Thanks, Obi. Cheers. Do I have to use this?
No, you have one.
I'm okay, right? Okay, sweet. Hello, thanks for coming. Right, just 2 seconds to get set up. That's, yeah. Do we have internet? I see. Okay, good. Okay, good. Present. Okay. Now present. This is kind of annoying, actually. I'm gonna change it so we're just one screen. I always have to keep looking backwards. Display. Don't mirror. Okay. Thanks. Okay. Good. So Obi's given us a bit of a brief history for the social context in which we find this technology. Most of what I want to cover today is concerning a very sort of new iteration that I'm working on, Jam, as is mentioned. But I want to sort of continue a little bit of contextualization by talking a bit about Polkadot and a bit about where we find ourselves in this wider industry. So the industry, the sort of blockchain, Web3 industry is increasingly sort of moving in, forking in sort of two directions. Broadly characterizable as sort of long-term versus short-term thinking. And I think the sort of only the first set is really following in the sort of footsteps that Obi's laid down and described in that historical context, and certainly is in line with what we sort of saw with Bitcoin and what we pioneered into Ethereum. It's important to understand that not everything in this industry is particularly, even the stuff that calls itself Web3 is particularly in line with what Web3 really is. A lot of corners are increasingly cut, and a lot of secondary interests are increasingly taking primacy. These terms are not equivalent. They are related, but they're very much sort of different terms. Don't think too hard or don't think too much that Web3 is about any particular resource or technology, and certainly vertical. It's really not. It's a much more sort of, I suppose, abstract and abstract longer term concept than any particular use case. And one of the phrases that I've tried to associate with Web3 is this: less trust, more truth. Why? Surely trust is a good thing. Well, the issue doesn't look right. Not sure why that's bad, but anyway, there we go. Why less trust? So when we choose to trust something and that trust pays off, that thing behaves as we expect it to behave, yeah, it's generally a good thing. And this is why we generally say it's quite nice to have trustworthy friends, trustworthy institutions, trustworthy companies, because they are worth our trust. They honor how they present themselves. But the issue is that trust essentially implies a lack of self-sovereignty and self-potency. Like we only do something, we only trust someone in general is because it's too hard or too time-consuming or too not part of our sort of core competencies to do it ourselves. And in general, we would assume that we would prefer not to have to trust third parties in order to do our thing. Now, if it's our friends and if we have or family or whatever, we have a very strong relationship, then that trust is, can be perfectly reasonable. But when we're talking about institutions where we may have very little choice, or governments where we have no choice at all, then trust can become a big problem. Trust generally implies, especially when we talk about these larger organizations, a massive power imbalance. And as we should know, if we're sort of know a little bit of philosophy, power is not generally something that we want to, or powerful entities are not generally things that we should be trusting. These slides are a bit screwy. Can I make this text visible? Yes, okay. Now we can point to a few recent examples, vaguely recent examples, of trust in these like very large centralized authorities being very problematic. But these are just examples. The principle carries through them and also carries through the course of known history. It's not a good plan. Now, the thing is, we build these institutions, these organizations, governments, because the alternative at the time was worse, right? Not having banks, even though you have to trust banks, was worse than having banks. But as we've built the internet and as we have increasingly good knowledge and understanding of game theoretic principles and of cryptographic principles, we're able to create viable alternatives for many different use cases to trusting these large institutions, authorities. And in part, it's by facilitating the sharing of truth, or facilitating also the gathering of truth. Now, we can talk about a few different sets of principles or words to describe what Web3 blockchain is. And a few different people have done it. I'm one of them. There's also Sean Tabrizi, who came up with the 5 on the left, and Andreas Antonopoulos for the 5 in the middle. And I think they're all sort of ways of dancing around the same broad concept. I'll go into my 5 a little bit later, but the point is that Web3 is altering how individuals, and to some degree organizations, can interact with each other and with the rest of the world. Blockchain, moving on from Web3, blockchain is really just a decentralized computer. It's a computer that doesn't exist physically, right? But that exists conceptually and is manifested through many different computers running potentially many different pieces of software to give a service that we would broadly consider quite similar to the service that we would get from a single computer. Okay. I guess I somehow broke the template of this. Yeah, because I copy and pasted slides. Oh dear. Okay, well, I'm going to ignore that slide. It's not so important. Now, the point is that this slide, we are moving forward in this technology, right? So Bitcoin sort of came along and said, well, here's how you do a decentralized calculator, right? With kind of a sort of a database. It didn't really have a database attached, but it did have, in principle, a means of detecting invalid transitions of some database, although the database itself wasn't sort of contained on chain in the same way that we did with Ethereum and so forth. Anyway, Bitcoin, kind of an accounting system, calculator. Ethereum comes along, sort of takes that and adds some, pretty good scripting capabilities, and a more generalized storage system, and turns it into a sort of computer. Polkadot comes along and sort of takes that. Now, the simile here is sort of an interesting one. It's in some sense, Polkadot came along and sort of created, we might call it a sort of tightly connected LAN of computers. Yeah, LAN of sort of single processor computers. We could also just about stretch it to saying it created a multi-core computer. Now, the reason I'm a little bit hesitant to say it's a multi-core computer is because it doesn't have shared memory. Most thing that you generally get with a multi-core computer is that there's a single memory that each of the cores can draw data from and write data to. Now, Polkadot didn't provide that. Polkadot provided essentially a sort of a multi-core processor, but with separate memories for each core. Yeah, and I'll come to this later. This is a key sort of difference. Now, Jam is building on what Polkadot created, but it's relaxing this separation between the computational elements, between the cores, and in some sense, actually building a multi-core processor. Web 2, Web 3, what's the difference? Resilience is the key word here. Now, it's the first word, the first of the 5 sort of tenets or principles that I've made of Web 3. And I would say it's by far the most important of them. It must be resilient against quite a lot of different things, which is why I don't sort of say it's decentralized or cryptographic or anything like this. These are all means to the end. The end is resilience, right? There's a few other principles that we want as well, but resilience is the key one. And it's resilience against a whole host of potential malevolent powers in the world. Right, so building how do you build a cloud? Well, you kind of need a computer to build a cloud. So if we're going to build a cloud, we first need to start with a computer. That's really where Jam comes in. Jam is a means of building a cloud because it provides this quote-unquote supercomputer. Now, this is in the context of Polkadot, and the idea is, of course, that Polkadot will be upgraded to have the Jam protocol in due course. Okay. So I had the two separate presentations, right? And I sort of just thought, I'll just copy and paste the slides from the first one into the second one. But yeah, it turns out that Google, even though it allows it, Google Slides is not capable of doing it properly. But it really looked like it might be. Okay, so the main resource of Web3. It's not the only resource, right? So Web3 has a few different resources, in the same way that computers sort of have a few different resources. One of them is block space, which you can think of as being secure computational capacity, really secure, right? Like secure that you can run a billion or trillion dollar economy through it, and it will still not get corrupted. Still, no one can corrupt it. No government, right? No organization, no malicious power can corrupt it. This is what we're talking about when we say block space, right? It's really, really secure computation. It's not computation it's not computation we would reasonably run on Amazon, right? Yeah? We're not going to run like, $1 billion finance system where a single alteration in a single piece of data could transmit, hundreds of millions of dollars from one person to another on a random Amazon server. Yeah, it's just too likely that some employee somewhere or some random hacker somewhere can flip those bits and steal $100 million. Right? It's just too likely. We are going to do something more secure. Now, block space is sort of the stuff, the computational resource that sort of Bitcoin uses in order to ensure that, despite it being a multi-billion, multi-hundreds of billions of dollars that's running through its economy, no one can flip those bits, right, and switch ownership of $1 billion here, 100 million there. There are different blockchains that are doing essentially the same thing, but with more functionality, different use cases. And the way that we measure block space, the way that we characterize it, is we can talk about how secure it is, how much data can be passed through it, how much data can be stored within it, how much computation can happen, under what latency, with what guarantees that at what points that it won't be reverted, that different inputs may be used. There's quite a lot of factors that we have to take into account. So it's actually quite difficult to compare two block spaces, right? Two different block space providers. Nevertheless, it is important to attempt it. Now, Polkadot's sort of ambition or mission in all of this is to deliver the highest quality block space across all of the factors. This is, and it actually does. That's the mad thing. It actually does. So there's a lot of different block space providers now. But if we actually look into trying to nail down how good each of these block space providers are, you look at a few different metrics, right? You can't look at, we can try and look at many of them. I'm going to pick out 4. First one is transactions per second, which is a pretty horrible metric, but because it's kind of like what does a transaction mean? But we sort of limit it to sort of account transfers from accounts that haven't actually been touched yet in this current, execution invocation, and or block, and we just count how many we can do, right? And in this case, this figure's from the Kusama network, which is a sort of a version of Polkadot. Still runs the Polkadot technology stack, and it peaked at like 140 thousand TPS, which, as you can see, blows the others out of the water. Then we can talk about how much information can we get from our general data store into the chain. Polkadot's case, again, substantially more, 42 megs a second compared to some of these single domain services. So they're not trying to do anything else like Polkadot is, right? These like EigenDA and Celestia, Avail, all they're doing is making data available, right? Specialized solutions, and they're still substantially lower in terms of the ability to pass data into a blockchain than Polkadot's inbuilt solution. We can talk about sort of decentralized and resilience in terms of the overall validator set. How many different independent economic entities do you have to basically bribe or corrupt or hack in order to break the blockchain, stall it, or make it do something it's not meant to do? It's like, you compare the majors, Polkadot is like miles away, right? 149 compared to the next one, Cardano, 29, 5 times as much. Ethereum is like 2 or 3, right? It's heavily centralized in terms of the economic entities that are validating it, that are its validators. Despite, it must be said, having an awful lot of keys, right? Ethereum counts over 1 million different validator keys. It's just that like 300,000 of them are controlled by the same entity. You look at energy efficiency, Polkadot actually distributes its workload in an efficient manner, right? Which means, and it does so by utilizing much lower processing power machines, essentially, cheaper machines to run, greener machines to run, and distributing its workload over them rather than having a bunch of super high power machines that just have to run everything more or less synchronously. I mean, technically, in Solana's case, it's not. They do actually use CPU cores to distribute some of the workload and so on. But like it's still, we're talking about very, very beefy machines which are replicating all of the processing. Each one is executing everything. Same with Ethereum L1. Same with most of these things, actually. So yeah, going back to that, how do we do it? Well, Polkadot actually has hundreds of execution, quote unquote, cores, right? Now, I'm not talking at this point about CPU cores, but they are analogous to CPU cores. They're just sort of virtual, right? We're not talking about a physical processor now. We're talking about this manifestation of a processor, but that Polkadot provides, that it gives, but it's a non-physical manifestation. It's still a virtual service. And it's got hundreds of execution cores. Actually, in Polkadot, not so much. But Jam will have hundreds of execution cores. Polkadot has like, I don't know, 40 or 50. Because it has multiple cores, it can parallelize its workload and distribute it across many different validators, right? This allows for the possibility of many different economies to pull together and share their security, yeah? Because essentially you have one single means of validating that everyone's work is correct. It means that you can have different economies tapping into that validation service, paying for that validation service from their own economy, and effectively sharing the cost of that validation service with other economies. This is what we call shared security. Yeah, and it's something that, for example, systems like Cosmos, which essentially have their own chain, so in some sense they parallelize the workload, but they don't share their security, right? There is no means of allowing those different economies to pool together and reduce the overall cost by sharing the workload. You can think of shared security as a sort of like a kind of NATO, right? If you want like a sort of, to imagine it, it's a sort of NATO for blockchain. And the idea is that if you make your security provision or your validation a common problem, you can reduce your costs quite substantially. Interoperability is an interesting one. It's something that Polkadot really has been pushing to bring. One of the projects that for Polkadot's interoperability is XCM, which is essentially a message format that describes the sort of thing you might want to do on a chain. And essentially by having a common language with which you interact with a blockchain, XCM, then you don't have to think too much about a chain's specific features because you just express something in this common language. And this makes chains more interoperable. For example, you might have two different decentralized exchanges, or even not decentralized, just exchanges on two different chains, each with their own sort of niches and functionalities and features and interfaces. If they can both understand XCM, the interoperability language, then you can use either of them. You can switch one out for the other, right? Essentially, it's a compatibility layer. Yeah. Now, Polkadot provides data availability, and it does so through its own data availability layer, and a very good one it is as well. And it means you basically don't have to deal with multiple tokens for different services, have additional costs. Data availability is something that basically everything needs, right? And when I say data availability, I mean high security data storage available to block space, right? So if we talk about block space as being this ultra high security computational resource, we can talk about DA or data availability as being this ultra high security storage resource. Good. Now that brings us on to Jam. So we kind of understand the context that Jam is coming from, I would hope. And now I'm going to talk much more about the specifics of the Jam protocol. So Jam stands for Join Accumulate Machine, reflecting essentially the job that the on-chain portion of Jam does. It's actually a shortening of the original acronym Core Jam, with the core part meaning collect and refine. And in reality, it actually still is collect, refine, join, and accumulate, but jam is shorter to type, so I just dropped the core bit. Good. Let's move forward. So, driving factors for jam. Now, I mentioned, these 5 terms before in the context of like what is Web3. And I mentioned resilience, the first of these, before as being what I consider the most important part of Web3, most important principle that distinguishes Web3 from, more traditional IT systems architectures in particular, and particularly Web2. There's a few others. Generality, which is essentially, as you might expect, the different use cases that it's possible to do, or it's at least practical to do on the platform. Bitcoin was less general than Ethereum, for example. I got performance, which is, in some sense, how much work the system can do, right, in any given time. And we may also bring in cost to performance as well in any given time for any given cost. Now we have the last 2. The first 3 are pretty easy. And we see, like, if you look for Bitcoin, Ethereum, Polkadot, you see a clear, well, all 3 are resilient. Bitcoin wasn't general and didn't have very high performance. Ethereum is more general, but still didn't have very high performance. And Polkadot is general and had high performance. So in terms of like the first 3, it seems that we're done, right? But actually there's 2 other things that are actually pretty important things to have in a Web3 platform. Accessibility is a funny one, but essentially it's sort of to what degree is it possible for people to actually use the platform, right? In terms of software, but also in terms of like literally like access to the RPCs and the APIs, applications that might be run on them. How easy is it to actually interact with the thing? Coherency is the degree to which the system exhibits coherent, so kind of synchronous behavior, right? So to what degree can we characterize the system as a whole? And given that with that characterization, how easy or how fast is it for any 2 parts of the system to interact with each other? And what's the difference between the ease and speed that any 2 parts of the system that you might choose could interact with each other? Now, if the system is like one big monolithic thing, like Ethereum L1, then it will be equivalent, right? Any 2 parts of the system, any 2 smart contracts, any 2 accounts can interact with each other just as easily as any other 2, right? It's homogeneous. And this is like pretty standard with synchronous systems. Synchronous systems tend to be homogeneous in terms of their coherence, fully coherent. As systems grow, become faster, it's harder to maintain coherence. It's harder to provide that guarantee. And it kind of follows, as you might expect. If a system grows, the distances between any pair of elements within the system will have a greater variance and will have a higher mean, right? It's just, that's the natural part of a system growing, scaling. And if we want overall interactions to keep going fast, then we kind of have to relax some of our coherency, yeah? And this is where we get to a problem. This is what Polkadot did, right? Polkadot relaxed coherency across the whole of Polkadot and said, well, actually, one parachain can kind of move and do its thing synchronously within the bounds of the parachain state coherently, and another parachain can do its thing at the same time. Overall, the system goes out of coherence, right? The 2 parachains have no idea what each other are doing at the time. The 2 portions of state can no longer affect each other. We've drawn a sort of causal barrier between our state, yeah? Now, we get toward at the end of our sort of period of processing, and we have a synchronization event. Essentially, parachain sort of checkpoint, and we come back to the center, and they can potentially exchange messages or whatever. We get a recognized single coherent state of the whole of the system before, for another period of time, 6 seconds as it happens, the system moves forward, but with each of the portions of state doing so independently and without reference to each other. The system becomes incoherent again. This is a way of managing, right, our reduction in coherence. We have what I've called a partitioning, but a fixed partitioning, right, or a persistent partitioning. We have partitioned state along parachain boundaries, or our L2. If you're not familiar with the term, it's just our L2 blockchain atom. And we don't allow, within our general processing time, we don't allow these pieces, these portions of state to interfere with each other. We have partitioned our system, and we have fixed how our system will have a reduction in its coherency, right? How it will be incoherent. And how often that incoherence will disappear, and we'll end up with a coherent system again. Good. Now, this is where jam comes in, right? As you might have expected. And this is the thing that jam is aiming to fix. And I'm going to be sort of talking about, have this theme in mind for the rest of the presentation. Okay, now, rewinding a little bit back to resilience, I want to talk about the jam approach, because it's a little different to what we did with Polkadot. It's much more in line with, and indeed extends from what we did with Ethereum back in 2014-15. Now, jam approach centers around 3 main initiatives: the grey paper, which is its formal specification; the jam prize, which is essentially a bunch of money for people that implement its formal specification; and the jam toaster, which is a purpose-built machine which can simulate jam, full jam network at its full scale, and allow experimentation and optimization and so forth. Essentially because it's in a very controlled environment. All right. So yeah, the grey paper follows on from the yellow paper. It actually uses similar, to some degree, similar notation, similar structure, similar format. But it's somewhat longer. It's actually, I think at the moment, the yellow paper is 40 or 50 pages. The jam paper is like, 65-ish. So it's actually not that much longer. And it's, there's still a good amount of text explaining what all of the formalism mean, but yeah, it's not the easiest read. The jam prize is as I said, it's like a prize pot for implementations of the grey paper, right? So the grey paper details essentially 2 important things. We can sort of split jam up into 2 sort of parts of the protocol. One of them is the quote-unquote on-chain portion, which is essentially when a new block comes in. Blockchains are just a sequence of blocks. When a new block comes in, evaluating if the block is correct, and if it is correct, what it means. This is, broadly speaking, what we call a full node. Right? Full nodes are able to interpret blocks. They maintain a database of the state of the chain up until now, and they are able to interpret full blocks and update their state database and determine whether the block itself is valid or not. This we give for any implementer. If they achieve this in line with the specification, we give them the first milestone prize importer, block importer. The second prize, block authorer, is the ability to produce new blocks and do so sensibly. In principle, you can just produce empty blocks, but this isn't so useful. The ability to sort of take information that's floating around on the network, provide information to the network, and similarly use the information in order to create new blocks and pass them to everyone else on the network. It's the second milestone. block authorer. After that, there's no more functionality that's needed. Right? So it's kind of like you got all the hard work with the first with the first 2 milestones. You're passing all the conformance tests. The last 3 milestones, well, the 5th one is security, right? Basically passing a security audit. The 3rd and 4th are about optimizations, right? Making it go fast. So it turns out optimizations pretty important. And if the node doesn't go fast enough when it is authoring blocks or importing blocks, the network is it's going to have problems. So we essentially going to reward implementations that can run more or less at the same speed as Parity's implementation, and roughly the speed that we expect through our modeling, the network should be able to run at. Beyond, if you're passing these milestones, beyond getting the prize directly, there's a bunch of other useful things that you would benefit from. Salaries for developers within the team, potentially like professional audits, invitations to seminars for with other teams and me, protocol designers and so on. Toaster access, hardware provision, and potentially also sponsorship for being part of the Polkadot Fellowship, which essentially gives you some degree of ownership over the protocol itself. In order to just not have everyone implement it in Go and Rust, there are a bunch of different languages that have sort of been grouped up, right? And the prize pot has been split between these groups. So, for example, at the moment, I think there's like 7 or 8 different implementations all in Go. Well, there's only actually a certain amount of dot that those implementations will be able to draw from for their milestone prizes, right? Whereas there aren't so many implementations coming from language groups C and D, and therefore they are much more likely that if they all make it to milestone 5, that there will still be ample funds left in the pot for them. Moving on, the Toaster is, as I said, a purpose-built computation resource that is actually capable of matching expected hardware requirements for the whole Jam network. So that's 1,023 validator nodes, but in a single centralized resource for doing experiment. I'm not going to run Jam on this like production, but we are going to simulate Jam on this and experiment with Jam on this. And it's not much compared to today's supercomputers, but it's a pretty hefty bunch of machinery, and it's it should run quite quick. Okay, moving on. What is Jam? Well, I'm going to contextualize this with some of the other things for comparison. Polkadot, which is available now. You can play around with it. It's been on its project. I guess it was launched 4 years ago, a little over 4 years ago. Now, as I mentioned before, with the key issue that we've found with Polkadot is that state is partitioned persistently, right, between its L2s, between its parachains, which makes it, while it's easy for any individual parachain to interact with itself, it's not as easy for 2 different parachains to interact with each other, right? So if you've got a smart contract in one parachain and a smart contract in another parachain, it's not so easy for them to interact as if they were both in one parachain. Now, this isn't specific to Polkadot. This is a general issue with having different blockchains for your scaling mechanism, right? And I'll come on to what other systems suffer from this as well. Polkadot also, to some extent, suffered from some high barriers to entry, in particular parachain slot auctions. That's been fixed with Agile Core Time now, for those who are aware. But there still exists some high barriers to entry. Polkadot's primary abstraction mechanism, the primary means that teams in Polkadot put forward launch their service, bring some extra functionality into Polkadot, is through creating a new blockchain. And creating a blockchain, deploying it, maintaining it, is not something for the faint of heart. It's not as easy as coding and deploying and maintaining, in general, a smart contract. Now, of course, you can do a lot more with a blockchain, a custom blockchain, than you can with a smart contract. But not everything needs all of that extra stuff. So, okay, let's compare it to Ethereum. Now, Ethereum is a bit of a moving target. In fact, it's a lot of a moving target, so it doesn't make that much sense to compare to. I mean, we can compare it to Ethereum as it stands, the L1, which hasn't really changed very much in the last 10 years. We can try and compare it to kind of Ethereum plus its various patchwork of L2 chains, but then it's like kind of hard because they're all kind of different, and it's not clear really how many of them are actually Ethereum and how many are just sort of extra chains that sort of run on the side. In general, Ethereum is quite costly. It's quite slow. It turns out that things have moved on quite a lot since 2014-15 time. And taken together with its L2s, it's very patchy. Different L2s do their sort of scale their computation in different ways, provide different guarantees, different chain extensions. There's different levels of centralization, different tokens, different ways of communicating. So it's kind of becomes rather difficult to consider Ethereum sort of as a whole. And at least for ZK L2s, we see a huge amount of centralization because of the need, essentially. I mean, there's a few different sort of factors in this, but one of the main ones is the huge amount of processing power required to produce proofs of correctness, and it doesn't make sense for every node on the network to be able to arbitrarily produce a proof just as fast as everything. It doesn't make any economic sense to produce a proof as fast as any of the other nodes. You can look to bridged chain systems, one of the notable ones being Cosmos. They pioneered this. Bridged chains essentially say that, well, we'll just have lots and lots of different chains, and they'll each have their own validator set, and they'll each have their own economics, and they'll each provide their own security by essentially feeding their economics into their validator set. And then we'll just have a sort of a very easy way of setting up bridges so that we can sort of send messages between chains. Yeah, the issue is it's insecure. If we have this like cause effect relationship of sending a message over a bridge, we need to have fairly solid guarantee. Well, we need to have, in order for the receiver to act upon the message, they have to be certain that the message really did come. I.e. that the sender of the message, they can believe that at the moment it looks like it has come, but they can't be certain that in some particular period of time it will still have come, that there won't have been a chain reversion. How could there be a chain reversion? Well, if it doesn't cost that much to buy off 2/3 of the validators, then they can just issue new confirmation messages and have the validators create a fork and go off on the other fork. Of course, it's even worse if they use something like Bitcoin, where you don't even need to like forge messages or create double-signed messages. You can just create a separate proof of work chain. But the thing, I'm not going to sort of dwell too much on the insecurity aspect, although it is very, very important. I also really want to point out that this suffers from precisely the same issue that Polkadot comes from with its persistent state partitioning. The different chains find it very easy to interact within their state, but very difficult to interact between two states on different chains. Now, Ethereum, I didn't mention this, I just realized I should. When I say patchy, it suffers from the same thing. Ethereum's L2s find exactly the same problem. Very easy for if you've got two smart contracts that want to interact, if they're deployed on the same L2, easy, right? If they happen to be deployed on different L2s, hard, right? We still have this problem of a lack of coherence. Now, the odd man out here is the high-performance synchronous chains, essentially souped up validator nodes, generally not very many of them, oftentimes highly centralized. These provide a single state environment, fully coherent, essentially a very fast version of Ethereum L1, but they tend to be very fragile, centralized, and ultimately unscalable, right? There's a sort of ceiling, which is how fast can you make a validator node go and expect other validator nodes to be able to keep up, right? And ideally pass the baton between them so that you don't have a censorship issue. Yeah, we already sort of see the limits of this with networks like Solana that are demonstrably fragile, right? And already push the validator requirements to a level where it's not really a low barrier to entry anymore. Yeah, not everyone can run a validator at all. You're going to have to be pretty specialized to be able to do that. All right, so Jam. How does Jam help? Well, I'm gonna talk a little about what Jam is first, and then I'm gonna sort of go into how it helps solve this issue. Or am I? Maybe I'm not. No, I will. Right. So Jam expands on the core model. What I've called this, like the idea of scaling out over many different cores, parallelizing and distributing workload over a node network. And it's the same thing that Polkadot's done, right? It's the thing I was harping on about 20 minutes ago, why Polkadot is good. But the thing that it brings is to try to reduce the level of decoherence, right? By relaxing this hard, persistent state partitioning that Polkadot does by splitting everything into parachains, distinct L2s. And the same thing, by the way, that Ethereum is currently setting its sights to do with native rollups. And the same thing that various other chains have done with their subnets and various other terms for essentially saying another blockchain that we will try to secure, yeah, L2s. Well, Jam is essentially a way of saying, let's get rid of the whole L2 thing and just provide the resource that you need to validate L2s without actually sort of sleepwalking into this assumption that it will be used specifically to validate independent blockchains. Because maybe if we do this, we can work out a better way of managing this incoherence that we kind of have to we know that we kind of have to manage because we want to scale out. Now, Jam, the way that it manages this decoherence, the way that we kind of say, well, how do we scale out then? How do we know that we're going to have to sort of make some portions independent, for at least for some period of time. How do we know which portions to do? Well, we kind of have this two separate computation phases, right? We have an in-core phase, which is stateless, essentially, apart from access to this distributed decentralized data lake, essentially a data availability store, right? A big storage pool, yeah? And then separately, we have an on-chain portion, which is fully synchronous and fully stateful, right? So it can read and write from a database synchronously, in essence. And these two are connected, right? So data can flow from in-core to on-chain, and it can also kind of flow back again on-chain back to in-core, but it does so with a latency. The basis of these two things, of this sort of controlled coherency, or controlled slight transient decoherency, is refine accumulate, right? So refine is the function name, essentially the name for the execution process that happens in core, and accumulate is the name for the execution process that happens on chain. And a single service or a single piece of software that is deployed has both the refine part and the accumulate part, right? So first, when data flows into it, into a service that you've deployed, first it goes through refine, gets processed in this mostly stateless, but with access to this data lake. And then the result of that gets pushed into accumulate, which then happens, its execution happens on-chain, synchronously, statefully. In principle, data can be shared between the different cores using this data lake. So you can, one core, one sort of portion of work can write information in, write data into the data lake, and then later another core can read data out of it. There's a few other services, data services available as well, but I'm not going to go too much into those. They're kind of needed for doing Polkadot compatibility. Now Jam is projected to host 341 of these. Now, okay, before I go into this slide, I'm going to restate this, but I'm going to do so from an Ethereum person's perspective, right? So I'm going to use different language, different terms, but it means the same thing. Jam hosts, okay, I'm going to give you a little bit more information, 341. There are 341 cores, all right, or these parallelized distributed computational elements. That's kind of similar to CPU cores. They are L2 native rollups, 341 of them, right? Native rollups. And they each sort of synchronize with a smart contract L1 chain, right? The rollups have common access to a DA store that is 1.6 petabytes big. And this DA store gets synchronized with a 6-second latency. So after 6 seconds of writing to it, you can read from it, and the data that you've written to it will definitely be there. If you happen to be running on the same core, the same computation element, the same L2 index, this reduces to 0 latency, which is to say, if on a core you write to something, then in one block, then in the next block you try and read back from that, it will always appear to be there, right? It's not, you don't have to worry about it. It has a number of protocols behind it, one of which is ELVS. This is a research paper on ELVS where they prove that it's sensible. I call ELVS, which I think, it's a fine name, but I think in Ethereum terms, ELVS would be called a cynical rollup. So we have this concept of an optimistic rollup, which I think is actually better termed a pessimistic rollup, because we kind of assume the worst, which is to say we don't pass the message on until such a long time has passed that it's almost certainly fine. Right? But we take a very pessimistic view because we actually wait for such a long period of time, right? We're not very proactive in attempting to find out if this work is valid. Cynical rollups are much more proactive, right? They're not pessimistic. Rather, they just accept that they're probably that there are certain things that we can do that will allow us to gain confidence that the work is valid or not sooner. It's not pessimism, it's cynicism. Like, we still believe that there are malicious actors out there, but it's just that we have a much better way of dealing with them because we know them better. We have a couple of consensus protocols, not too dissimilar. I mean, somewhat dissimilar, but like in the same rough ballpark of security and latency. Safrel and Grandpa, I'm not going to go too much into them, but they're fun if you're interested in that sort of thing. So if you want to visualize the join accumulate machine, Jam, essentially you've got like an outer portion, which sort of goes in and out of decoherence. Because you have sort of independent computational elements. And then you have a thing in the middle, the sort of in Ethereum terms, the smart contract L1, but something I call sort of the reactor, because it sort of reacts together all of the outputs from the computational cores on the outside. And that's where everything becomes coherent. Now, the reason that this transient decoherence, the reason it's sort of more useful with Jam is that it's firstly, it's stateless. So it's not that any particular portion, any particular core, any particular part of this computation, any particular computational resource is tied to particular state. It's not, right? It doesn't care what it works on. It draws from the same DA, and otherwise it's stateless. And that's a sort of really key difference here. And because it's drawing from the same DA, it's a bit of a silly picture, but the point is it's sort of data is able to be passed around between cores at different time slices. So each of these slices, each of these sort of petals, flowers, is sort of a different time slice. And each of the petals represents a different computational core. And the point of this diagram is to show that actually it doesn't matter which core processes which data, mostly. There is some affinity between data that's been recently written from a core and how fast you'll be able to read it back. But beyond that, it doesn't matter which core you're on. Okay, so what service does Jam provide? Well, it's if you look at Jam's state, the state is arranged into services. Now, this is the on-chain state, not the DA state. The DA state is just like basically a big lookup for 4K blobs of data. Essentially, you just throw 4K blobs of data in, and you can look up 4K blobs of data back again. On-chain, which is the synchronous database, the thing that's always fully coherent, we have we have services. Services are, as I mentioned before, they have 3 code entry points: refine, accumulate, and then this other one, on transfer. On transfer is the thing that essentially manages interactions between services. So if a service sends a message to another service, this on transfer gets called by the destination service, right? On the destination service. Refine is the thing that does basically all the computation work and all the heavy data lifting from the data store, right? It sort of grabs things together, does lots of work on them, and then eventually passes this sort of distilled result into accumulate. And then accumulate sort of does whatever is needed to check that maybe everything was correct with refine. With refine's provisional inputs, any assumptions that refine made, maybe accumulate needs to check those assumptions, and then otherwise integrate it into this coherent state. And this is how we're managing the fact that we have this coherency problem that we somehow have to manage, right? This is essentially the structure of how Jam is decoherent, is incoherent in some sense. So Jam is permissionless. Anyone can upload services, right? You can write a service, which basically involves writing a refine, an accumulate, and an on transfer, right? Just 3 pieces of code, and then upload it to Jam in the same way that you'd upload a smart contract to Ethereum, right? Just the same. There's no sort of immediate limits placed on how big the code can be, how much data can be stored, anything like this, how much data can be processed even. These are only economic disincentives, right? So it's like if you're willing to pay the money, then you can put as much code in as you want, you can store as much data as you want, and you can do as much computation as you want. An example of what a service might be, and in fact, one of the things that Jam was designed to facilitate was Polkadot One, right? We want to take the parachain service, or the ability to host L2s, right? And make that a service, right? That's one service. One service is like the whole of Polkadot. That's the level of sort of abstraction that we have with services, right? Jam is Jam is focused on providing these sort of smart contract-esque services. It doesn't care about any of this other stuff, right? So staking, economics, and governance, it's totally agnostic to. Like different instances of the Jam network, of Jam networks, may have their own staking mechanism, economics, token issuance, blah, 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 governance. Jam doesn't care. That's not the point of Jam. So I said smart contract-esque things. They're not quite smart contracts, but they are a bit like what maybe we can liken them to smart contracts. The main points of difference are that there's pipelined computation. So you have this refine and then accumulate pipeline. There's actually another element in the pipeline, which is sort of payment for the thing. Smart contract platforms will generally have gas fees to pay for execution of a smart contract, of a transaction. Jam services don't have gas fees, but I'll come on to that in a second. There is instead a sort of bulk purchase of this computational resource, or bulk purchase of gas, and they are asynchronous, which means they can't be services directly can't be synchronously composed. One service cannot call into another service and wait for a result. Rather, they will send messages to each other, and those messages will be processed asynchronously. Okay, so the service pipeline, we have refine, accumulate, and managing transfers. That's the last three bits. By now, I would hope sort of reasonably clear about that. There is actually an initial phase of using a Jam service, which is authorization, right? We want to authorize the work to be done. This is, if we look to Ethereum for the alternative, it would be paying for the transaction, right? So the transactor will pay some gas at some particular gas price, and that authorizes the network to run the transaction, right? To do the work. Jam doesn't work like that. Instead, because Jam also wants to support the Polkadot model, Parachain's model, which is where a parachain will pay for a month of its operation, and they will just probably buy a whole core and just say, right, I want all of that core for a month. And then essentially parachains will resell that core under their own economy. Yeah? So we want to facilitate both models in Jam. And so we have this quite general authorization mechanism that separates the purchasing of the computational resource of core time on a core, from the usage of it through code. So actually write code that when you buy a service, when you buy core time, you associate code with that core time, with that time on the core, and then that code can be run by Jam to check to make sure that whoever is trying to use that core time is in line with what the purchaser wanted, right? The rightful owner wanted. And by doing it this way, we can facilitate secondary markets of this resource, core time, right? Time on a Jam core. This is already underway with Polkadot, and it's under the broad sort of, if you want to read more about it, it's called Agile Core Time. All right, moving back to the Jam service model. So as I mentioned, there are three different phases in when we execute a single, if you like, send a single datum into a Jam service. So like what we would generally call a transaction, right? Now in Jam, it doesn't really make sense to call it a transaction because it's not signed and it doesn't have a gas associated, well, it doesn't have a gas price associated with it. It might lead to confusion. So in Jam, it's just called a work item, an item of work. And you send the item of work into a Jam service, and basically up to three things happen, at least the first two: refine and accumulate, right? Refine accepts quite a lot of data, 12 megabytes of data, up to, and it yields only 48 kilobytes of data, right? So it can work with up to 12 megabytes of input data. These 12 megabytes can come from two different sources. One, they could just be extrinsic data, so data just associated with the work item. You just include the data with the work item. You can totally do that, and it's no problem. Or you can have, for any amount of that data, have it be read from the distributed decentralized data lake, right? So you can just like actually have your work item sort of read data magically out of the data lake. And you can split it whichever way you want. As I say, it yields up to 48 kilobytes of data, and it should execute for about 5 seconds of PVM gas, Polkadot's virtual machine, PVM gas. PVM I haven't talked about yet, but I will try to get onto it in the not too distant future. So it's going to execute for quite a long time, up to 5 seconds. This is way, 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 way longer than what you would expect for a transaction on a smart contract, right? Really, really long. And for what it's worth, PVM gas is much, much more efficient than EVM gas. Orders of magnitude more efficient than EVM gas. Yeah, there's a few other bits. One of the most important parts of Jam is that inside of Refine, we can create new PVMs. We can create inner PVMs, new instances of virtual machines. Yeah? And we can set them up however we like. And because the PVM specification is sort of totally contained state virtual machine, including the stack, it means that just by knowing what is in a PVM's addressable memory, we can essentially recreate an instance of that PVM at a later time. In essence, this allows us to suspend a PVM instance and restore and continue running a PVM instance across blocks, right? We can create continuous virtual machine environments over multiple blocks. This is quite a big deal. PVM itself is a RISC-V derivative. It's sort of changed in order to facilitate and optimize for recompilation onto the x64 platform. And this means, because RISC-V is supported as a target for LLVM and compilers, you can kind of compile any code down to PVM and then execute the code from inside of the blockchain, right? Inside of Jam block space. And if it takes longer than 5 seconds, don't worry. You can shut down the inner PVM and just restore it on the next block. From the perspective of the code that's executing, nothing has changed, nothing has happened. Yeah? Now this allows a class of software to be executed on-chain that hasn't ever been possible before, because up until now, you have a really hard limit, which is your block gas limit, and you can't execute anything more than the block gas limit, and you kind of have to start from scratch in the next block. Plus, you're dealing with virtual machines that are really made for scripting cryptographic operations with mad register sizes like 256-bit or being stack-based architectures, and really not made for executing sort of regular code made by regular languages on regular machines. This all changes with the PVM. Right? The PVM is custom designed to be actually really quite similar to x64, just a lot simpler, but able to be recompiled in linear time into x64 code. From our experiments, we've found that you can execute code approximately 50% of native speed. So if instead of compiling your code to x64 and running it there, if you compile your code to PVM and then recompile it from PVM to x64, which is, as I say, a linear operation, even including the recompilation time, it's still about 50% of the speed that you would get for native, right? Now this is huge. If you compare this to like EVM execution, native versus recompiled. Again, we're talking orders of magnitude and difference of execution speed. Okay, so invoke inner PVMs. Big thing, big change. Now, accumulate takes the output of refine. In some sense, you can look at accumulate as a sort of atomic database operation. Yeah, you can look at refine as basically being an application's process, right? So just the application sort of running along, pootering about, exporting stuff to DA hard disk, importing stuff back from DA hard disk, managing its VMs, right? And then you can look at accumulate as being this sort of shared synchronous database that's scriptable. So you can have your script that sits in the database, like actually on the database side, to ensure that your different processes that are all sort of part of the same application don't step on each other's feet, right? And all actually obey roughly like the same rules and assertions and so forth. That you can kind of see accumulate as that. It's in technical specifics, so all of the various refine outputs, because we might have multiple refines, right, running in parallel, distributed over our node network. These outputs get sort of collated together, yeah, and fed into a single accumulate invocation per service, per time slice. This means that accumulate can, in essence, interpret all of these outputs in whatever order it wants. Yeah? There might be some particular order that it needs to interpret it in, because as far as, like, for example, if we're writing a Polkadot, an L2 validator, then its accumulate function would probably want to go through each of the L2 chains and make sure that it's processing, if refine is the thing that's checking the chain's transition, like each block, it would want to process those updates in the order of the blocks. It wouldn't want to process a later block of an L2 before an earlier block, right? It would want to process them in order so it can, for example, check that the parent hash actually does refer to the previous block. If it processes them out of order, it can't do that because it might process a later one whose parent hash doesn't point to any block that we know about yet because we're not, it's coming in later. Now, accumulate gets to basically order these things as it chooses. And therefore, things like transaction ordering are not important in Jam. Like, there is no real concept of like validator MEV, like validators choosing which transactions in which order to optimize for their own or potentially malevolent forces' economic benefit. It's like the service itself, like the smart contract itself, gets to choose the order. Everything just sort of comes in as one. Accumulate doesn't get to operate for as much time. I mean, we're looking at refine, maybe 5 seconds of PVM gas. With accumulate, because it's synchronous, it's 10 milliseconds. Because we're dealing with 341 different pieces of work items that need to be processed in accumulate, and we guarantee synchronous behavior. We guarantee that each will get its time and not step on each other's feet. So we're kind of stuck with having this relatively short amount of time. Thankfully, PVM gas, as I said, is very, very efficient, and therefore 10 milliseconds does actually allow you to do quite a lot. As I mentioned before, it's stateful, so you can transfer funds and do all sorts of alter state, and it's all good. And it can also create services at breakcode. There's a few other things that you can do in accumulate. I'm not going to go too much into it. And then there is on transfer, which basically is the same as accumulate, but is just for handling transfers. One of the things that we might do in the future, a future alteration to the Jam protocol, is try to amalgamate accumulate and on transfer into the same thing. So when you, for example, transfer, maybe accumulate actually gets given the last accumulation's transfers as well as new work items. But this is sort of there's a few open questions for this, so I'm not sure yet. It's a classic diagram. I'm not going to go too much into it, but you can kind of see there's the inputs and outputs at the sort of left side there. feeding into this big piece of computational machinery, PVM core. One other thing I didn't mention with a PVM, it supports metering, dynamic metering, which means unlike for Polkadot where we don't have metering, and this is a bit of a pain because we have to do things like benchmarking, which you'll know about very well if you've ever tried to author a parachain. With Jam, that's all goes away, and we have dynamic metering, which means we know how much computation, roughly how much time has been spent on something resembling an x86 processor, just inherently as part of it running. Yeah, good. I think there's two. I don't want to go too much into that. So this is going back to the authorization system. Now, as I mentioned, work on the Jam core is expressed as, well, work items. Work items are bundled into work packages. A work package might just have one work item, but the idea is that it can have a few of them. You might want to use different services sort of in the same work package. There is at any given time at most one work package on one Jam core, on each Jam core, right? If you like, a work item is a bit like a transaction because it's like data that goes to a Jam service. A service is a bit like a smart contract, and a work package is like a sort of tranche of transactions that execute synchronously, execute in the same computational element, the same core. I don't think it makes sense at this point to go into core time, so I'm not going to really talk about that. I've already talked about it a bit anyway. Okay, now, what is this all pushing towards? And this is the sort of new bit of the talk. So if you've seen Jam talks before, you haven't seen this bit. CorePlay is what might be called Jam's signature service. Now, one of the first services to be developed on Jam is the Parachains service, or the Polkadot 1 compatibility service, right? And this will allow Jam to validate L2s on Polkadot parachains. But this isn't especially, I mean, there's a few things that this facilitates, like avoidance of benchmarking and a few other bits, but this isn't the main benefit that Jam brings. The main benefit that Jam brings is not, as I've been laboring now, is not having to have this fixed, like persistent state partition, right? Dividing up state between parachains and then not allowing them to really interact very easily. CorePlay is designed to utilize Jam's various functionalities in order to provide a more agile state partitioning mechanism. So, before going into this, I want to ask a question. I'm going to answer it for you. I already did. You can see the answer. What does it solve to have more chains or more L2s, right? And you know, we've played around with a few answers. As Polkadot was a pioneer in this, right? With parachains as heterogeneous multi-chain system. And you know, we talked about a few. I talked about a few things: specialization, sovereignty, right? Scale. In reality, if you have the right smart contract system, you don't gain anything in specialization, and you don't gain anything in sovereignty, right? If you have the right, not all smart contract systems can give you these guarantees, but some potentially can, at least. But you will get scale. Having more validators, doing more work, processing more information, holding more data will give you greater scale. That's the problem that is being attempted to being solved with more L2s or more chains. And the big problem with that approach is fragmentation. If data lives on one chain, it doesn't live on another chain. Yeah? Now, of course, you can say, well, we can oracleize it in there. There are ways around this to some degree, but they are fraught with issue. They are suboptimal. And generally, there's still fragmentation left at the end of it. Generally, it's still much easier to interoperate within a state partition, than it is to interoperate between state partitions. The reason I mentioned it twice is a joke. There's the sort of strip. Don't know how many people here have seen Red Dwarf, but one or two. Good. So, all right. So, what's the big problem with fragmentation? Well, it limits an awful lot of things that went unlimited in the Ethereum L1 heyday. Limits network effects, right? It limits use cases. It mostly limits use cases by limiting atomicity. So you can't really atomically combine different services across state partitions. It doesn't really work. I mean, again, I'm sure like someone clever can come up with a very roundabout way of kind of doing it if you have this assumption and that assumption and you don't do this at the same time. But it's like, it's a pain, right? It limits it, if not precludes it completely. It limits developability because, again, you're dealing, as we know very well from Polkadot, you're dealing with, when you're dealing with sort of different state partitions and systems are split across state partitions, you have to resort to sort of interoperability workarounds, XCM being a very notable one. And because you have to essentially select which state partition to deploy into when you are wanting to develop and deliver a service, it forces you to decide up front without knowing if what your market. It's kind of like, okay, I can only choose one country to have my company in, and I don't really know that well. It's going to take me a year to develop my company and start selling things, and you don't necessarily know in advance which country is going to be the best environment. It's kind of like, I don't know, deploying launching a blockchain without like doing any legal research or knowing where any country is going to be in a year's time, which is sort of the situation now. So I think this is just bad. It would be so much better if we could just deploy it, to the platform, and not worry about like which avenue of the platform, which L2 of the platform. So, core play. And the idea of core play is to scale smart contracts without fragmentation, right? Without persistent state partitioning. The smart contracts are, I put them in quotes because they're not really smart contracts. They're better than smart contracts. They are actors. But you can sort of, you'd be able to take a smart contract, like a Solidity smart contract, and build it into something that you could deploy in core play in this actor environment. There's a few different points of difference between smart contracts and actors, but in general, I mean that actors, by actors, I mean firstly things that can be asynchronously as well as synchronously composed, but also serious code in there, right? Not Mickey Mouse stuff that we often find in smart contract systems, but like significant amounts of state, maybe a significant, multiple significant databases that they have access to, real functionality. Core play should be, the clue's in the name, it should be scalable across many different cores, right? Jam has 341 cores. It doesn't make sense to only use one of them if you've got a burgeoning smart contract ecosystem. We should use as many as is needed to keep the price as within economic sensibility. We want to provide through core play the same level of global atomicity that a single smart contract homogeneous environment, like a single state environment, non-partitioned, would provide. This is like a kind of mad thing to try to achieve, because it seems that it would disagree with the general thing of like, well, as you scale, you lose coherence. But the idea is that we draw our state partitions dynamically so that actually we're not attempting to provide atomicity over everything all at once, but only atomicity for the things that need it when they need it, all right? So it's kind of like partitioning things into sort of different quote-unquote chains. Chains isn't the right word, different L2s, I suppose. but we're choosing which bits of state to partition. And the state, because the state can move freely between the cores at any given block, as we've just spent a while talking about jam, one of the things that jam does, this means that we can, in principle, achieve this apparent global atomicity. The apparent ability for any 2, 3 or 4 or however much smart contracts or actors to actually sit with each other and synchronously compose, right? To make function calls into each other, mutable function calls into each other. And thus we achieve zero fragmentation because you no longer need to select a state partition. Yeah? We no longer have this fragmented ecosystem. So how do we do it? Well, first and very importantly, we have this data lake, right? Distributed, decentralized data lake. This is the thing that allows the different actors to basically move seamlessly between computational elements and reconfigure themselves into different partitions for synchronous composability. We have pipelining. This pipelining isn't such a big thing, but it does significantly increase the amount of computation that we can do. But it's not so relevant to CorePlay as much as PVM. PVM, as I just mentioned, has this ability to host continuations, which means our actors can, as far as they're concerned, they just got a continuous process going. Yeah. Now they get woken up and sort of scheduled when it's economically viable for them to be scheduled, but other than that, they sort of go to sleep. And we start to get something that looks much, much more like jam sort of being a piece of hardware and CorePlay being the sort of operating system that sits on the piece of hardware. We have this kind of split. And I sort of, thus far, have really focused on jam because I want to talk about the hardware, right, virtual hardware. But I think it's starting to become time to talk about the operating system that will sit on this hardware. And that is CorePlay. So it works by basically having much smaller state atoms, right? Actors rather than blockchains. Regular repartitioning, so we can take these state atoms and regroup them as we need to, as is economically best. And indeed, we have this sort of co-scheduling thing, which co-scheduling just basically means facilitating synchronous composability by putting the actors or the state atoms in the same core, in the same synchronous compute element, rather than across different cores where it's hard for them to interact. Okay, so compare it to a few other approaches. One approach is and these are basically Ethereum-centric approaches. One of them is to have just multiple instances. Why don't we just have multiple dexes? Right? We just have the same I don't know, Uniswap or whatever, but it'll just sit, there'll be one on this L2 and one on that L2 and one on that L2. Well, I mean, that's obviously a very good branding approach, but it isn't useful for actually having, scale. Like, you're still going to have just totally independent dexes. Doesn't actually help anything. Then you can imagine that, well, maybe we have a rebalancer that sort of every block or two tries to sort of even things up, so they're kind of synchronized. If that dex has gone a bit off in terms of its exchange rate, then we sort of move something from there over here until the exchange rates are sort of equal. But unfortunately, this still is sort of problematic. It's still not going to be not give a particularly good solution. The resources will always be divided because they live in different states. Yeah. Also, for what it's worth, rebalancers are not particularly general. They work well with a few particular financial use cases, but that's about all. Okay, what about co-sequencing? Well, actually, co-sequencing isn't a bad thing. For those of you who don't know, it's basically like taking two sort of authors, like authors for different systems, in this case, block authors, and actually having the same agent author into those two systems. Because it's the same agent, they can, in principle, make they can entangle effects, right? So they can have some cause over here, have on one system, have some effect over on another system, and vice versa. As long as they can be certain that both of the blocks will not only make it to their blockchain that they are responsible, that they correspond to, but also be finalized on that blockchain. And now we have quite a lot of, there's a lot of problems with doing this. The biggest single problem is that blockchains are huge. They're big, big state systems. And if you have co-sequencing across blockchains, then all of the co-sequencers need to know everything about all blockchains that they're co-sequencing across. If you have 341 blockchains, that means you need a single validator node that speaks to all 341 blockchains and knows everything about them all and can make, what various optimization consolidations between and how these blockchains should be combined. Furthermore, in principle, you're still kind of screwed because the chains, you kind of have to track the entanglement of causality across the chains. Basically, if you've got 341 chains that you're trying to combine block production for, then each one of those chains has 340 other chains that any effect it's going to take is dependent on being final, right? And again, if you've got just a sort of God validator that whatever they say goes, and they guarantee that if any one block gets into any chain, all of the other blocks will definitely get into all of the other chains. Yeah, okay, kind of might work. But this doesn't work in general, right? And you've got a sort of order n squared problem of all chains need to track pretty much 340 other chains sort of finality and certainty of accumulation or integration of effects. This all leads to massive amounts of resources needed. You have to have validators, or you have to persuade validator nodes on all of the chains to sort of use you as their block producing agent. It leads to huge centralization. And this is, again, what we kind of see with these systems. Now, intent solvers are another interesting sort of approach. Intent solvers are essentially a way of specifying that you don't care which chains are used and what transactions are sent, simply that you want a particular thing to happen. This account may be reduced by this amount at most, and at the end of the transaction, you'll check that that was the case. And you want to have at least this NFT deposited in some other account. And you will check that that's the case. And the thing is invalid unless that's the case. And they're powered by what are called they're powered by intent solvers. They're powered by nodes that understand how to use each network and understand what each constraint is, what each task is. So essentially you need a combination of tasks and networks, or providers that sit on networks. And you would need to write a sort of task, a task implementation for any given provider system, any given network, for your solver to be able to utilize that in some potential solution. This essentially turns it into an order n squared issue, right? Because you've got sort of two different things and you need all pairwise combinations of them. It's also not an especially general solution. It only works for the tasks that are that can be expressed. It doesn't work for random smart contract functionalities that might be quite novel. And it also doesn't fix the fundamental issue that we're trying to fix, which is that the providers or the smart contracts or the services that sit on chain themselves may want to actually interact directly with each other without going through this off-chain intense solving system. Okay, one thing that you don't see mentioned too much in JAM is ZK. In fact, ZK is used in JAM. It's used in the Safrole system, but that's not utilizing ZK for scale, but rather for privacy, and through privacy resilience. Why not? Well, JAM actually has this ELVS thing, cynical rollups, I've also called it. And ELVS just beats ZK when we're trying to scale computation, right? And it's the cost compared to performance of crypto-economic systems like ELVS are just way outperform ZK systems for scaling. Now, of course, ZK is the various ZK technologies provide very elegant mathematical abstractions for doing this sort of thing, like the idea that you could sort of compress a proof of correct computation and have it be evaluated, with orders of magnitude less computation is kind of cool. Like it's very easy to see how, from a mathematician's perspective, ZK would be very attractive. But in terms of a sort of shrewd business person's perspective, it doesn't make sense. For what it's worth, it costs about 2 million times as much to guarantee correctness using ZK as it does using ELVS, right? And that's assuming that you sort of use regular cloud services and using the PVM as a benchmark for it, and the latest of that we could find anyway of public ZK performance numbers. Now this is going to reduce over time. There's already plenty of work happening in the ZK world that is probably going to take this 2 million X premium down by a few orders of magnitude, and eventually it might be as low as maybe 50K premium. But there's quite a good blog post by Rob Habermeyer, one of the old Polkadot co-founder and one of the old Parity devs, on comparing what ZK will likely bottom out at over time compared to crypto-economic security mechanisms. And the expectation is even with significant improvements in ZK, it's still not going to be a match or even close to a match for scaling computation. It does have some advantages beyond scaling computation, like no great need for data availability, but there are factors as to why you might want data availability regardless of whether you need it to prove correctness. You may just want it in order to, for example, avoid censorship of future transactions within your system. So, I mean, it's overall, ZK at present at least doesn't provide a particularly attractive prospect if we care about the economics of the system. If we are pure mathematicians, then maybe there's some attraction there that us mere mortals don't see. Good, right, I'm gonna do a Q&A, and then if there's any time, I don't know, then I'll do a demo as well, but cheers.
All right, thank you so much, Kevin, for your presentation. Then let's do a quick Q&A, one question per person. So who wants to start, Richard?
Great talk again. How easy is it to spin up a service? Can I sort of contextualize it like having specific palettes for a specific service, or how does it work?
So it's a service is pretty similar in nature to a smart contract. I will answer it by giving a demo, since it's not too difficult. Right, can we see that? Yeah, just about. I'll increase the size a little bit. This is a service. this is my test service. So we have 3 functions, as I mentioned before: refine, accumulate, and on transfer. All they do is a very simple storage write. So refine, refine doesn't have storage, so it doesn't do any writes. It just takes its input payload and concatenates hello space onto the front. Accumulate goes through all of these work outputs, and for the ones that actually were without error, and sets the storage. In fact, so only the last one is actually going to have a storage set after it because it uses the same key for each one. Last, and just sets it to that data. And then on transfer, if it receives a transfer, it will, for any transfers received, it will make a nice message and again set a storage item, in this case last tx, to that message, just describing the transfer. So this is like a very obvious, simple service, but it's not too hard. Now this was previously compiled and built into a little test version of Jam that I have here. Can we see that a little bit? Not much. Maybe I can make it bigger. Ah, yes, good. Okay. So I can have a look at the service. This starts with a Genesis that's like a development Genesis with 2 services. It's got one of them is the test service. I think that's at 0. And it's, code, the test code. It knows what the test code looks like, which is exactly this. This has just been compiled into this executable. And service 1, which is the Bootstrap service. This is a special service. It's a more substantial service that has a bunch of sort of instructions that you can give it to do things like create other services, write, export data, a few other bits, like does quite a lot, make transfers. So we can read a service's storage. So the service, in this case, index 0, which is the test service there. And I will read last, which is the thing that it writes to when it gets a work item. Then I'll make a guarantee work item. I'll have to cheat and see what I forget actually what the parameters are. Guarantee work item, where are we? REPL. REPL. Guarantee work item is in here somewhere. Here we go. So service, payload, and core, but core's not required. So service and payload, that's easy. So I'm going to send a work item into service 0, and the work item will be Cambridge. And so what we've done, there's an authorizer. In this case, it's the null authorizer. This is associated with all of the cores in the development instance. This basically means all work packages, when they get fed into the system, just always are allowed. System is allowed to compute any work package, regardless of what it is. You wouldn't use this in production, of course, because it would just be susceptible to spam, but it's fine for development. It's a bit like having the gas price at 0 or something. And then we see it's printed a message saying it's in the refine with payload length 9. 9 is the length of Cambridge there. It's guaranteed a work package. It's got accumulate has found it. That's good. So it's looking all good. If we read, actually I think we've got it. Yeah. So if we read there, then we've got like hello Cambridge. So it's passed through refine. It's put hello at the front. Passed that into accumulate. Accumulate's written it to storage. And we have is a as I said, service 1 is the Bootstrap service. There isn't a way of creating services directly. Like you can either put them in Genesis, or you can hope that something already on the chain has some functionality allowing you to create services. But there isn't, like in Ethereum, if you don't specify the destination, I think, then it will create a smart contract for you. It's sort of like a special transaction type. Jam doesn't have that. In Jam, it's very pure. It's like, if you happen to make a Genesis block that had no services in, it would be totally useless because there isn't a way of creating services. But anyway, we have this Bootstrap service, a bit like a sort of BIOS, right, on a regular PC, that lets you do anything that you might need to do. So one of the things that you can do is transfer And then again, I'm just going to cheat here and look at what the transfer thing is. So we have destination, amount, gas limit, and memo. So the destination, we're going to transfer to our test service, which we know is at index 0. The amount, we'll give it 42. What would you go? Gas limit, let's give it plenty of gas. And a memo, which we'll say is money for nothing. Okay. And looks like it's succeeded. So we guaranteed this work package. It's attempting the transfer. Looks like it's got an OK back. So let's have a look at last TX. If you remember, this should have been written to by the test service, and there it is. Transfer at slot 4 from 1H is like the service that it came from, service 1, which is the bootstrap service, to this service, 0H, of 42, and there's the memo. So, yeah. Cheers.
Hello, my name is Annie. Thank you for the presentation.
You're welcome.
Just out of curiosity, the Polkadot virtual machine, how does it compare with things like in Amazon, like EC2 sort of thing? And I also understand that the Polkadot also sat in the cloud. Do you use like cloud suppliers like AWS or Microsoft Azure? How does it?
No, so the PVM is a instruction set architecture. So essentially, it's the blueprint for a machine. In our case, it's only a virtual machine. We don't expect any actual hardware processors of supporting PVM to ever be produced. And this is because we've built it specifically for recompilation into x64 and some of the other like ARM instruction sets. And it's highly unlikely that anyone coming along attempting to produce processors that would support PVM natively would actually outperform on a sort of price basis x6 like AMD and recompilation to its architecture. So Jam could potentially be compared, not rather than PVM, to Amazon sort of cloud services. The comparison is a bit questionable because we're really talking about Web 2 versus Web 3, and Amazon cloud services don't give you that level of security that you would, you wouldn't run Bitcoin, like the whole Bitcoin network and a Bitcoin authority on Amazon. You wouldn't entrust Amazon to run it for you and just trust that they're not going to alter something in their favor. Like, the whole point of Web3 is that it's resilient against authorities, that it's resilient against centralization, it's resilient against special interests. Yeah. But if you wanted to, you could compare Amazon like EC2 with Jam in some sense. They both provide computational resources. One is Web3 computational resource, one is Web2. And Amazon run EC2 as a whole is far more powerful than what the Jam network could do. Again, the quality of computation is very different to what the Jam network provides, or a Jam network would provide. But if we want to get into and one other point of note, Amazon EC2 provides you with independent server instances. They are not meant, they don't provide you with a coherent sort of state space in the same way that Jam does. Now you can combine it with like shared object stores and you probably get something not too far from it. But nonetheless, it's a little different. It's like you have distinct machines with cloud providers like Amazon, whereas you have a single coherent or mostly coherent environment with Jam. What else? There is the way that you would scale Jam, like a Jam instance out, so that you actually are able to utilize more Jam instances, would be through what I've sort of termed the Jam grid, or a Jam grid, which is many different instances of Jam, each connected to the other instances and able to allow their work output, right? So this the bit of data that gets passed from refine into accumulate to actually be sent around the network to other instances. What this allows you to do is to select any jam instance, run your kind of services refine code on there, and then have it forward the output onto another instance where the service actually lives and have it accumulate. This, in principle, allows your service, without you doing anything particularly special, to elastically scale, not just over a single jam instance, but many jam instances. And then it's a question of, well, how many jam instances could we run? And, I mean, pretty much as many as you want. It kind of scales indefinitely from there. You do need bridging. So for every new instance that you add, you would have to add a bridge to all of the other instances. But we have like pretty good designs for lightweight bridges. So this probably isn't going to be a particularly big issue for at least like the first 1,000 jam instances in the grid. Beyond that, you probably want some multi-hop mechanism where, not every jam is bridged to every other jam. But to send, and if they happen to be a multi-hop, then it's, one jam would forward another jam's refine output into the third jam's accumulate input. But I mean, I think we're at a point now where it's not the sort of thing that, I think once we get to 1,000 jams, anything that you would want to do in a consensus environment, like with block space, you're going to be able to do that in this jam grid. It's a lot of Amazon instances are used for a lot more than doing like consensus level computation. Like you wouldn't necessarily do AI training. I mean, you wouldn't do AI training in a consensus environment. There is no need to have consensus on the fact that AI is, well, maybe in the future there really is. But for now, performance is far, far, far more important than consensus over the specific training data being used on this specific model. Similarly, like video games, it's not like if you're talking about real-time video game networking, it's not that important that you, if you've got like a game of Capture the Flag being played sort of globally, that like it doesn't necessarily have to go through a consensus environment. The value for doing this is so low that you probably don't need to send it via a blockchain. Yeah. So not everything that we do on like EC2 at the moment is stuff that we would want to do inside of a blockchain. But for the stuff that we would want to do inside of a blockchain, we're probably sorted with 1,000 jam instances. I mean, never say never, but like it's 640K ought to be enough for everyone. But like it's an awful lot compared to what we have now. I think I calculated it. It's something like 1 or 2 Ethereum L1 capacities for every single person on the planet, right? So it's like every person has an interoperable Ethereum blockchain for themselves, just their transactions. And this seems like, enough, probably.
Thank you very much.
Hello.
Sorry, my name is Jean-Pierre Bell, and I found what you were talking very thought-provoking. So one of my questions for you is, when do you look at extending it beyond the 12 megabytes? I know that's big compared to what we have right now, and I agree with you. If you're doing a game, consensus doesn't make sense. But if you're doing finance, things like trade finance, this is where data isn't necessary. And the idea of being able to orchestrate it this way seems to me somewhat easier when you're looking at self-sovereignty, not only at the individual, but also at the country. So what are your thoughts in terms of being able to have more data, or are you always looking at the breakdown of the data and bringing it back up to see if it?
No, you're absolutely right. Like data is almost certainly going to be the bottleneck rather than processing. I think processing power is pretty handy to have, but if we look at like the improvements from taking Ethereum L1 as a benchmark, the multiplier that we can get on processing power is substantially more than the multiplier we can get on data availability and data bandwidth specifically. Now that 12 megabytes is a hard, per work package, is a hard number to increase. Essentially because it's data that has to be sent to not every node, but many nodes within the validating network. Enough nodes that we can be reasonably certain that no malicious force can make it seem as though the data is there when in fact it's not. And this limits us, if we want to distribute our workload across a node network, we're limited in a very hard fashion by the transmission speeds, the data transmission speeds we can expect of a reasonable validator node. So if we say, well, actually you've got to have a 100 gigabit link to all of the validator nodes, then we can just make it 100 times. We can increase that 12 to 1200, right? Pretty much, yeah? But the issue is that if we do that, then we're basically going to have to require validators to be co-located. And then we got centralization. And I mean, 100 gigabit bandwidth is not cheap. So we're kind of, again, limiting it to validators that can arrange for this to be installed, that can put up the upfront cost. It's hard. Like, if we want this to be an accessible, decentralized, with diverse validator operators and a diverse geolocation of nodes, then we have to keep it, we have to keep the barriers to entry relatively low, relatively standard. Now that all said, the way to increase the 12 megabytes isn't to think about it, isn't to try and increase the 12 directly. Of course, over time, our average resources reasonably available to a validator will increase, and the 12 will increase with it. But until then, it makes sense just to use more cores, right? It's 12 megabytes per second, per 6 seconds, 2 megabytes per second per core. If what you need to do requires more data, use more cores. And if you run out of cores, then that's great. That means we're doing something right, and we need to add more jam instances and start building the grid, right? And then, because the overall data bandwidth is 341 cores times 2 megabytes per core, so that's 682 megabytes per second per jam instance. And if you need more than 682 megabytes per second, you create more jam instances.
More questions?
Do you have any other question?
Service, and in most situations we need more than one service per system. Let's say we do the governance system, insurance system, for example. Every 6 seconds, distress synchronizing, right? How can we, let's say, launch multiple cores and still keep the services synchronized? Because we need both read and write operations. So how would we be able to communicate cross-threads? Now the way I understand it is you can do this communication every 6 seconds. Does that mean the block is not final until those 6 seconds is passed, or how does it work? How does it work exactly?
Okay, I think I understand. So, the sort of deep synchronization does indeed happen notionally at the accumulation stage. Services don't live exactly on chain. In some sense, they have a better way of thinking about it, I think, more helpful at least from the point of view of developing services, is to think of the accumulate stage just as a sort of database that they can do atomic operations into. So they can write information into the database, and they can read information at the point that they are altering the database, they can also read from the database. Yeah? And they have to sort of bulk up 6 seconds worth of of computation before they do this single sort of database script, right? Now, if you wanted to let two services interact within these 6 seconds, that's hard, but not impossible. Now, it's hard because if the services exist on different cores, the whole basis of our transient decoherence pattern is that they don't get to interact because they are on different cores. If they happen to be scheduled on the same core, then it becomes possible, right? In fact, it's actually possible on different cores as well, but you need a sort of Ethereum hack, right? This co-sequencing like hack, right? Where actually it's the same work package builder, right? It's the same author that is doing the work for both of the cores and is making the entanglement that way. But if they happen to be on the same work package and therefore executing on the same core, then you already sort of have the entanglement built in because each one can actually look in to see what the other one's doing. In principle, you can have essentially synchronous composability. Like one service, they can't call into the other one I mean, one service's refine code can call into another service's refine code in this way. I call this sort of causal entanglement because it's like the two are now like causally related. You can't have one's effects without also having the other one's effects. So it's important to enforce this all the way through the chain, right? Essentially all the way into accumulate. But because we know that if one refine operation went through in the work package, that the other one will go through and they'll both lead to their according accumulates, then in principle that entanglement is already sort of enforced by jam. There are a few caveats to this. You have to make sure that accumulate is infallible. So it must be impossible for one of the refines to make the other refine do something that would prevent it from being accumulated and therefore would prevent its apparent effect, its apparent sort of causal effects from taking place. But I've introduced a sort of rough in some of the jam literature and a separate term for this problem, or to help reason about this problem, which is integration. And the concept of like actually integrating the effects of this causal entanglement into a service's state. Because we're looking at a pipeline, right? We're looking at this like refine that's stateless and it happens up front, and then the data goes into accumulate. But then accumulate does something to the chain, right? It registers something, or it acts on a message, or it puts a message in a queue, or it transfers a balance. Now, whatever logic happens in this accumulate is based on what happened in refine, which might be based on what happened in some other services refine, which we might hope to imply will something will happen in that service's accumulate, causing it to do something. For example, there might be a sort of cross-chain, cross-token swap, and sort of the refine of two entangled services both agree to swap equal and opposite parts of a trade to the other one. Yeah. Well, if it gets from refine down into accumulate, and the accumulate says, right, well, I know that this other services accumulate is going to transfer me tokens, so I'm going to transfer it tokens. Then, I mean, that's great, but if there's some way of it not transferring that service tokens, then there's a big problem. For example, maybe some other work package came in, and they're some mutually incompatible, mutually exclusive, and it selects, for whatever reason, it selects the other work package instead of this work package and just disregards the accumulate of that work package. Then there would be money for nothing, and that's an issue. How do we manage this? Well, there's a concept of integration, which is essentially like a sort of the effects that you expect from accumulate. If we call this the integration into a services state, then we can have a pattern whereby we would make a transfer to the other service, not of funds, but of a message saying, I am ready to send you funds. You send me a message saying you are ready to send me my funds, and whichever one, when we both see a message from the other one, only then do we do the fund transfer. Yeah? So essentially there's a synchronization point in Accumulate as well as in Refine. Refine does the sort of bulky synchronization, and Accumulate does the sort of, right, this is it. Are we going to do this? Yeah? And as long as they both agree to do it, as long as they basically both agree to have seen the same Refine, then it goes ahead. Yeah? And this is a pattern that I would expect to see in, if we try to combine sort of core play with the parachains primitives and like actually have those guys try and do synchronous composition between each other, but also potentially for actors in core play. So you want to make sure that like actors' effects that are co-scheduled all take place as expected, and that one doesn't sort of not. Now this will depend a lot on the implementation of core play, particularly the Accumulate implementation, but there's a possibility that we will want something like a sort of integration gate, right? Whereby either both happen, or if it's multi-party, many happen or none happen. This sort of atomicity guarantee that we sit at the very end of Accumulate.
Okay. Yep. Thank you very much for your questions and for answering those, Gavin.